So we're going to be talking about performing stoichiometry with solutions. So originally we introduced this idea of, oh, we need to measure with mass, convert into the number of molecules that there are, see how those molecules react, and then convert back out to get the number of the mass that we get out. So we're going to do the same thing here with solutions. There's a parallel. We measure mass before, now we measure volumes, and that tells us a number of things. So we can do stoichiometry with solutions as well. So we can do stoichiometry. Let's do a limiting reactant problem. So we have a reaction here, solid magnesium reacting with hydrochloric acid. There's a demo I used to do on this. I used to do this a demo in class, which we can't this year. I have a video of some other people performing this demo. We have solid magnesium, and we put it in a solution of hydrochloric acid, and that reacts to make magnesium chloride and H2 gas. You can fill up the balloons with H2 gas and see how much of the reaction has happened. So we have 200 milliliters of a 0.5 molar solution of hydrochloric acid. Magnesium is added to 4 flasks in the following amount. In flask 1, 0.0125 moles magnesium. Flask 2, 0.2025 moles magnesium, 0.05 moles magnesium, and 0.1 mole magnesium. So in each flask, which is the limiting reagent in this reaction? So what we'll do is, we don't need to know each of them. Let's just figure out how many moles of magnesium metal are needed to completely react with 200 milliliters of a 0.5 molar solution of hydrochloric acid. So we've got 200 milliliters solution, and let's convert that to liters because we've got the molarity. So milliliter solution, ooh, that's a funny 0. Let's be clear that this is milliliters of solution. And milliliter solution, and then we also have the concentration in that it's 0.5 moles of HCl per 1 liter solution. This is per liter solution. Liters solution cancel, and we get out, once you do the calculation, 0.1 mole of HCl. And now looking at this stoichiometrically, then one mole of magnesium is stoichiometrically equivalent to 2 moles of HCl. And so 0.1 mole of HCl 1 mole of HCl, 1 mole of magnesium, 2 moles of HCl, that gives us 0.05 moles of magnesium. So remember, beaker 1 was 0.0125 moles of magnesium. So in that case, the magnesium was limiting. In beaker number 2, 0.025 mole magnesium. Again, the magnesium was limiting. For number 3, that was 0.05 mole magnesium. Aha! If the reaction goes to completion, neither is limiting. There's exactly the right amount. The 4th one, we had 0.1 mole of magnesium. And so in this case, the hydrochloric acid was the limiting reagent. So what else could we do here? Well, in each case, since we know the limiting reagent, then we can figure out how much hydrogen gas evolved. So if we think about the balloons, so if the flask is on top of a balloon, then this one, the magnesium's limiting, then we're only going to get a small amount. For this one, got our flask here, the balloon's gonna have essentially twice the volume. And then in this case, I'm not a great artiste. So it would be bigger. And then finally in the HCl, then in that case, it'll be the exact same size because the same amount of reaction will occur. because here we have an excess of magnesium, and so these two reactions, we get the same amount of gas being produced. But in the first two, the magnesium is limiting. There's less magnesium, there's less produced. So this really, really is not very good for demo drawing it like this. It's much better we can do it in person. So at least you've got the video there. So we've got nice balloons that you can look at. But that's the idea. So we can do solution stoichiometry. We can figure out the amount of products. We can figure out the amount of excess just the same, because we can go from volumes to moles. Okay, so let's look at other cases where one might be interested in doing solution stoichiometry. Titration. So titration is a very common type of quantitative analysis in solution used to find precise concentration of a solution, generally of acid or base, via the neutralization reaction between acids and bases. And we'll talk a lot more about acids and base in chemistry later, but for now on, we'll assume we're dealing with strong acids and strong bases, and they react completely. So you have some acid, like HCl, it gives up its hydrogen, reacts with the base, NaOH, and produces a salt and water. And so what you have is you have a dye that's an indicator that changes based on the pH, that changes color at the equivalence point. So when you start out, it's either very low or very high pH. You add stuff, and once the reaction goes past completion, it switches from acidic to basic or basic to acidic, depending on the way you're doing it. And the color changes, you go, aha, I've added exactly the amount I need to neutralize that reaction. So at the equivalence point, the number of moles acid is equivalent to the number of moles base, if it's a simple monoprotic acid reaction like this one is. So strategy, you take a known volume of acid solution with an unknown concentration. You're doing analysis here. You're trying to figure out what is the concentration of that acid. It's easy to measure the volume, but the concentration, that's harder. So you gradually add a known volume of a base with a known concentration. And then when the indicator changes color, the original amount of acid equals the amount of base added. So you know how much base you've added because you know the equation, you know how much acid there was to begin with. And if you know the initial volume of the acid, then you've got the initial concentration. Okay. So let's warm up. Let's do a simpler version of this. So we have a reaction. In this case, we have a sulfuric acid reacting with sodium hydroxide to produce sodium sulfate and H2O. Now, one thing you always have to watch out with whenever you're given an equation, is it balanced? And we can see right off that it's not really balanced because there's 2 sodium on one side and only 1 on the other. So in this case, we're going to balance it by visual inspection rather than doing the algebra. This is pretty simple. If we add, if we add 2 here, then, and we add 2 to the H2O, then everything is balanced. You can go through and see that that's all we need to do. And now we look at the problem and see it's not quite a titration problem. This is one step simpler. What volume of 0.25 molar sulfuric acid is needed to fully neutralize 50 milliliters of 0.1 molar sodium hydroxide? Well, what is unknown here? What's unknown is the volume. We have the concentration of base and the volume of base. We got the concentration of the volume of base, which means we know how much base there is. And we know there's a full neutralization. So the amount of base is stoichiometrically equivalent to the amount of acid. We've got the concentration of the acid. All we need to know is the volume we need to add. So let's first figure out how much base there is. So 50 milliliters of our solution, 1,000 milliliters, 1 liter, times 1 liter solution, and 0.1 moles sodium hydroxide. And so that is giving us, we have a volume of solute times a concentration of solute. That's giving us an amount of base. All right, we cancel out this. Just being very explicit here, solution, milliliter solution, milliliter solution. And so this is a number of moles of sodium hydroxide. All right, so now we know that 2 moles of sodium hydroxide is stoichiometrically equivalent to 1 mole of H2SO4. And so now that gives us a amount of H2SO4. We multiply by 1 liter of solution, because we want to cancel out on the bottom the 0.250 moles of solution. So these moles cancel, and we get out 0.01 liters. Convert it to milliliters just to be tidy. 1 liter, 1,000 milliliters. We get 10.0 milliliters. 10.0 milliliters of our sulfuric acid. That's the amount of sulfuric acid that is needed to fully neutralize this amount of base.